what's happening, everybody? Welcome to Earth Science. So this lab, going to tackle a couple things that feel a little bit chewy, but trust me, I'm going to take you through it. It's not that bad. What's our goal? We want to figure out what's up with these mid-ocean ridges and how they work. We're going to do a different lab for each of these plate boundaries you guys have been slowly learning. So yeah, I mean, there's a whole bunch of them, right? These all around the center of the oceans where new ocean floors being created and spreading out evenly. Here's a little animation of that. Where you look at it from the side, it spreads, fresh magma comes popping out, and moves on, creating a larger and larger and larger ocean, except in some cases where that crust then gets destroyed later on, but that's a whole different lab. So, that's the goal. Now, another thing that's kind of cool that pops up within it is what's going on with inside the Earth and our magnetic field. So, one thing we're going to want to have in our head to survive this unit, Earth's outer core is a liquid. Cool. That liquid is rich in iron and nickel, but iron's really the one that we're going to care about right now. And since it's a liquid and it's really hot and it's on the spinning Earth and it's dynamic and all this is going on, it is going through all of this churning and convection and pretty fast. And with all of that iron doing that and spinning and spinning and spinning and spinning, this induces Earth's magnetic fields. Now, that skips a lot of physics, and that might sound a little intimidating, but it's really one of the things we got to know out of it. Yes, it's a liquid. You can figure that out from the reference tables. It's a little tricky. It's got iron. That's written right in the reference tables. That part's easy, and it's the reason why we have a magnetic field. If you want to get into the physics of this, come hang out. Let's chat. But like, listen, it's not perfectly stable. It's a liquid inside of a spinning planet. So what happens is that Earth's magnetic north and south poles actually wander. And this has happened within human history. And if you've ever used a compass, that points at what our magnetic north is. That's not exactly the same as what our geographic north pole is. Do I have a globe? So when you spin a globe, that's our axis, right? That points right at Polaris, but the magnetic north pole that a compass points to is off from that a little bit. If you get into orienteering, you'll figure that all out and set your declination screw and all of that. But it moves really slowly, but it moves. And then what we've noticed, and this hasn't really been in human history, is that it completely reverses sometimes to where what according to physics is magnetic north goes down to our geographic south pole, and south comes up here to north. It'd be completely backwards. And then it flops again, and then it flops again, and then it flops again. It's longer ago than humans, and this is where you have to say all of human history, and my life is very short compared to the age of the planet. But it's happened, and it's happened, and it's happened, and it's happened. So one of the things that both like helped us figure this out, but it also unwrapped what is going on with plate tectonics, is that mid-ocean ridges, and this really should say, this is a bad sentence, this really just should say ocean floor is whatever, made out of basalt. Mafic igneous rock, which has iron in it, and that's actually what we're going to say here, which is mafic, if you remember your rocks unit, and contains iron, and iron is magnetic. So it's like every moment that igneous rock forms, mafic igneous rock with iron in it forms, you get a record of the strength and orientation of Earth's magnetic field at the time. And as it turns out, this is how we've discovered it, that it's been flipping and flopping all the time. Now, this is most often represented in like diagrams that you'll see with like stripes. Now, there's not literally stripes on the ocean floor. Don't worry about writing these if you don't want to. There's not literally stripes on the ocean floor, but that's how we represent it in diagrams to say that we notice that here is normal orientation, normal magnetic, like what we're used to, where north is north, and then it flops, and then it flops, and then it flops. And the whole trick to this lab is really just that. And it's the idea that right here at the ridge is where we see brand new. There's rock forming there today, somewhere along the mid-ocean ridge. And then as you work your way out, the rock not only progressively gets older, but symmetrically gets older in both directions. Older, right? And that's the goal of the lab, is to see that there's a symmetry on either side. And you're going to see the Regents loves this concept. They ask about it over and over and over again. The answer to that one, symmetry. The answer to that one is symmetry. The answer to that one is symmetry. It's just going to happen over and over again. That they symmetrically spread as you go out, and that the new is in the middle, and they get older as you go out. Now, how was this discovered? This looks intimidating. Don't worry. And it kind of is. It's a college-level lab that I stole from a lab book. What we're going to do, you're going to need 3 separate colors in Cami. And the first color, I'm choosing green. You do you. And I'm not expecting it to be perfect because I am clearly not doing it perfectly. 1 is going to be right on that dotted line, and that dotted line is the mid-ocean ridge. So MORS, which is mid-ocean ridge system. And now, I know I just said this, but keep this straight. That's where the brand new rock is formed, because new magma just squirted out today and formed some of that. Now, what this is an experiment that was done. This is, again, when we started discovering this, and it's 1966. I know that feels like a long time to you guys, but 1966, like, think of the other things we were doing then. The space program, we were working on getting to the moon, and we were just figuring out some of the stuff going on the ocean floor and how plate tectonics work. It's a relatively new science. And what we're going to do is that they would drag this device behind a ship, and it would record the way that the basalt of the ocean floor interacts with the magnetic field and give us these crazy readouts, and it's too much for us, right? So what we're going to do, the numbers have already been like interpreted for you. So all we're going to do, this is the whole lab, is connect 1 to 1 to 1 to 1, and then as a corollary to that, on the other side, 1 prime to 1 prime to 1 prime to 1 prime. That's in one color. And then pick a different color. Let's go dark blue for the 2s. 2 to 2 to 2 to 2. Ideally they don't touch, but clearly I just did, so it's not going to be the end of the world. 2 to 2 to 2 to 2. And now, whatever color you use for 1, go back to that, because that would represent like the flip and flop back and forth between normal and reverse magnetism. So my 1s and my 3s have the same number. 3, 3, 3, 3, 3, 3 prime, 3 prime, 3 prime, 3 prime, and now I'll go back to blue. My 2s and my 4s have my same number. And bang, lab done, right? You got to do a couple measurements, some easy things, but you can figure it out. And the point is that the new rock's in the middle, and we symmetrically spread. Deal? All right, I'm pretty much going to leave it to you. You got to do some measurements here. I acknowledge measuring on this is a pain in the butt, but you can do it. Use this little ruler tool and see, according to the scale, how far it has moved, whatever they're asking you there. Convert it to centimeters, and what you're going to do is see how fast the plate is moving in centimeters per year. It's pretty darn slow. This animation is preposterous, right? It's not done like to time scale. It's sped up. It's in time lapse to like let us see how it goes. You're going to see that it's only going like centimeters per year. And then, hey, if that map was published in 1966, and you know how fast the plate is moving, tell me how far it's moved since 1966. Not too far. And to say it again, the point of the lab is that there is this symmetry on either side of the line. See symmetry on either side of that green line. It's like a reflection. It's symmetrical on either side. So the answer to that one, that one, that one, that one, all deals with symmetry. That one, you'll see it over and over again. It's not as scary as it looks. You can do this. Just keep in mind what happens here as plates spread and the magnetic poles flip and flop. Best of luck. Take care.